Because the glomerular filtration rate is so important, the body has several mechanisms that help regulate the glomerular filtration rate. The basic mechanism of regulating the glomerular filtration rate depends on controlling the hydrostatic pressure, the pressure in the glomerulus. So this is looking specifically at the pressure in the glomerulus, not necessarily the pressure in the whole body. To regulate the pressure in the glomerulus, we can control constriction and dilation of the afferent and efferent arterioles. If we dilate the afferent arteriole, that's going to bring more blood into the glomerulus and increase the glomerular pressure. If we constrict the afferent arteriole of the glomerulus, then we're going to bring less blood into the glomerulus. That's going to decrease the pressure. This is assuming that we keep the efferent arteriole the same. If we constrict both the afferent and the efferent arteriole, we're bringing less blood into the glomerulus, but we're letting less blood out as well, and so that can actually maintain the same amount of pressure in the glomerulus. This we'll see is important for maintaining blood pressure even when blood volume goes down. Glomerular filtration can be regulated by neuronal control, signals from neurons or the brain, by hormonal control, signals from hormones, and also with a process called autoregulation, where a nephron can regulate its own glomerular filtration rate. We're going to look at each of these. Let's start by looking at neuronal control, which is going to involve signals coming from the brain and therefore affect the whole body. So both kidneys and all the nephrons are going to be affected at the same time. This is regulated by the sympathetic nervous system. And we've talked about the sympathetic nervous system a lot, so by now you should be able to quickly tell me that the sympathetic nervous system is activated when you're more active or exercising, and also when you're experiencing strong emotions, things like stress or fear or arousal or anger. All of these are going to activate the sympathetic nervous system. When the sympathetic nervous system is more active, it sends signals to the heart, we know, to increase the heart rate and the blood pressure, and it also causes vasoconstriction of blood vessels in the viscera to help keep the blood pressure up. That includes vasoconstriction of the afferent arterioles in the kidneys. This is going to decrease the amount of blood coming into the glomerulus, which decreases the pressure in the glomerulus, which decreases the glomerular filtration rate. So when your sympathetic nervous system is more active, your glomerular filtration rate goes down. And that's going to mean you're producing less urine that's more concentrated. The basic idea is you don't want to waste resources trying to filter out your urine when you need those resources for being active. The glomerular filtration rate can also be regulated hormonally. There are a number of hormones that, when they're released into the blood, go through the whole body and affect the kidneys. One of these is epinephrine. Epinephrine, remember, is basically the same as the sympathetic nervous system. When epinephrine is released, that's going to cause constriction of the afferent arterioles, decrease the amount of blood going into the glomerulus, and decrease the glomerular filtration rate, causing less urine output. A second important hormone is angiotensin II. We've talked about angiotensin II a little bit before. We saw that angiotensin II is important to regulate blood pressure, and it helps to keep the blood pressure up. The activation of angiotensin II begins with activities in the kidney, and we'll see that angiotensin II also affects the kidneys. Angiotensin II is released when the blood pressure is too low. This is detected by some special cells called the juxtaglomerular cells. Juxtaglomerular means next to the glomerulus. The juxtaglomerular cells are some special cells in the afferent arteriole right here next to the glomerulus. They detect the blood pressure in the afferent arteriole. When the blood pressure gets too low, that's a bad thing because that's going to decrease your glomerular filtration rate and lead to a buildup of toxins in the blood. So when the juxtaglomerular cells detect the low blood pressure, they trigger the release of renin. Renin, released by the kidneys, causes the conversion of angiotensinogen from the liver into angiotensin I. Angiotensin I goes to the lungs, where the enzyme ACE, angiotensin converting enzyme, converts the angiotensin I into angiotensin II. Angiotensin II, we've talked about before, is a very powerful mechanism for regulating blood pressure. Angiotensin II causes strong vasoconstriction throughout the body, which includes vasoconstriction of the afferent and efferent arterioles. The vasoconstriction of the afferent arteriole is going to decrease the amount of blood coming into the glomerulus, and that's going to drop the glomerular filtration rate. It would drop a lot, only we also see constriction of the efferent arteriole, which is going to help maintain adequate pressure, so at least we have enough glomerular filtration to keep from building up a lot of toxins. When we talked about angiotensin II before, we also said that it stimulates the sensation of thirst to make you drink more, and it activates parts of the sympathetic nervous system, and it also stimulates the release of aldosterone and antidiuretic hormone. These are two other hormones that are important for water conservation in the kidneys, and we're going to come back to those later. The last mechanism for regulating the GFR that I want to discuss is called renal autoregulation. That means the kidney regulating itself. What we're looking at here is local control of the glomerular filtration rate of individual nephrons. Each nephron has this mechanism to regulate its own glomerular filtration rate. Renal autoregulation depends on a structure called the macula densa. The macula densa is an area of specialized cells at the top of the ascending limb of the nephron loop. So this is after we've gone through the PCT, down the descending limb, and are coming back up the ascending limb of the nephron loop. That's where we find the macula densa. These macula densa cells can detect the level of sodium in the filtrate. Typically, a lot of sodium is reabsorbed as the filtrate goes through the nephron loop. So the level of sodium should be somewhat low in the filtrate by the time it gets to the macula densa. The macula densa detects the level of sodium and uses that to determine if the glomerular filtration rate is too high or too low. If you have a really high glomerular filtration rate, you'll end up with a higher amount of sodium at the macula densa because the fluid goes through the nephron loop so quickly there's not enough time to reabsorb the sodium. So there's more sodium in the filtrate. So high sodium is a high glomerular filtration rate. On the other hand, if your glomerular filtration rate is low, then the fluid is moving very slowly through the nephron loop, and there's lots of time to reabsorb the sodium, so the macula densa detects very low levels of sodium if there's a low GFR. If there's a high sodium level in the filtrate at the macula densa, which we already said means a high glomerular filtration rate, the macula densa causes constriction of the afferent arteriole. You can see how close the afferent arteriole is to the macula densa. It causes constriction, which is going to reduce the blood flow into the glomerulus and reduce the GFR. It's a great negative feedback mechanism. GFR is too high, macula densa detects that and constricts the afferent arteriole, and that reduces the glomerular filtration rate. On the other hand, if the macula densa detects a low level of sodium, which means a low glomerular filtration rate, then it allows the dilation of the afferent arteriole, which brings more blood into the glomerulus and increases the glomerular filtration rate. The nice thing about this is it allows each nephron to maintain a relatively stable glomerular filtration rate, even with changes in things like the blood pressure or the blood osmolarity.